Yes, yes,
Okay,
you are
okay. Thank
audible,
you,
sir.
sir. Thank you. Let's now move for our next session. The topic for the next session is composite materials in additive manufacturing. Uh, the expert will be for this session Dr. Hitesh Vasudev ji. Dr. Hitesh Vasudev is currently working as a professor in the School of Mechanical Engineering, Lovely Professional University, Punjab. He has received his PhD degree from Guru Nanak Dev Engineering College, Ludhiana in 2018. Recently, he has listed in a world top 2% scientist published by Stanford University and elsewhere in year 2023 and 2024. His research area include surface engineering, thermal spraying, HVOF, flame spray, cold spray and plasma spray, and microwave cladding. Currently, he is working on development of nano-structured, multimodal, high entropy loess coating for high temperature oxidation and corrosion resistance thermal barrier coating, and microwave processing of the materials. Dr. Vasudev has guided almost 10 PhD candidates. He has contributed extensively in thermal spray coating in reputed journals, which includes Surface Coating and Technology, Materials Today Communications, Engineering Failures Analysis, Journal of Cleaner Production. He has been awarded a top cited paper award in 2022 by IOP Publishing United Kingdom in the review category. He has more than 100 SCE and Scopus indexed papers. He has received a seed money for project titled Fabrication of Coating for Biomedical Applications. He also received a grant from Scientific Engineering and Research Board, New Delhi, Government of India, to conduct a conference. Uh, Tesh, sir, are you available?
Yes, yes, sir. Yes, sir.
Okay, over to you, sir.
Okay, sir. Sir, is my screen visible?
Yes, sir. Yes, sir.
So, good evening, all of you.
Good evening, sir.
So the today's session is composite materials in additive manufacturing. So here I'll be talking about the materials and uh, as I belong to a surface engineering background from research point of view. So here I have incorporated some studies related to the thermal spray as well, and the advancements of thermal sprays have already been added in this presentation, so that I can show some of the part from the additive manufacturing which has been integrated with the thermal spray. Dr. Hitesh, is full screen visible?
Yes, sir. Yes, sir. Screen is visible.
So here I am getting some messages. Okay, now full screen visible or not, sir?
Yes, sir. No visible.
Yes, sir. Clearly visible, ji.
Okay. Okay, so here I have added some of the applications of surface engineering uh, so that I can present additive manufacturing in my study, and we are also working on this part. So these are the contents. Obviously, 3D printing that will remain uh, because this is all about additive manufacturing. Then integration of additive manufacturing with the thermal spray, and then some of the basics related to the thermal spraying. So here are the RPT systems, rapid prototyping systems. There are three. So these are some basics: liquid, solid, and powder based. So in liquid based rapid prototyping, these are some of the manufacturers, you can say, which are right now working uh, with the equipments related to the liquid based rapid prototyping, and that equipment is nothing but a 3D printer only. So like 3D system is there, which is dealing with the stereolithography. Then Danken is one of the famous service provider in this area, and this one also Aeroflex. So these are some manufacturers related to the liquid-based rapid prototyping 3D printers. Then, similarly, in solid-based rapid prototyping systems, uh, so these fundamental principles like laminated object manufacturing, fused deposition modeling. So these are very common fundamental principles working behind the 3D printing in case of solid-based systems. And again, here some uh, manufacturers who are dealing with this one have been mentioned here. And then moving to the powder based system, because selective laser sintering is very famous in this category. So Z Corporation is there, three-dimensional printing, the provider of three-dimensional printing. Why Z Corporation is one of the famous uh, manufacturer. Then obviously here we are adding a material, and in case of conventional machining processes, we have to remove the material that comes under the category of subtractive manufacturing, and additive manufacturing, obviously, where we are adding some material. Then third one is the formative process, where we are changing the shape of the material by putting some stress into the material. Like bending stress is one of the examples. So where we are producing or manufacturing the various composites, various metals, various alloys by the means of bending. So bending machine is an example. There are n number of components which are used in automobile sector produced by using bending machines. So these are conventionally available materials where we are just changing the shape of the material. Then there is a process chain in case of 3D modeling. These are the steps. Like obviously we have to 3D model a product which we want to manufacture using 3D printer. Then data conversion is there. We have to check that, prepare that, and also once we are done with the fabrication part, then we have to perform post processing. So these fundamentals I already discussed in the first session, and in between there were many other sessions where these were discussed. Now, data transmission via these two formats are most likely considered, like STL and IGES. These are the two famous formats which are required in case of 3D printer. So in process chain, first of all, you have to prepare a 3D model by using dedicated softwares. Then you have to transfer that data into the computer linked to the 3D printer. Then in 3D printer, once printing is done, then you have to perform post processing. That is the fifth and last step of the process chain when you are dealing with the additive manufacturing or in 3D printer. Then STL is the first process. As I discussed, there are three. Here it is: liquid based, solid based, and powder based systems. So stereolithography comes under the liquid based rapid prototyping. That is the first example which I have quoted here: 3D system stereolithography apparatus, SLA. So here is the SLA. So what we are actually doing in this process, so uh, the part which we want to build, obviously there is some fundamental principle which is working behind that. And in case of 3D printing, the formation is obviously layer by layer. So we have to uh, look into the layers for the completion of the process. So each layer is being scanned by the optical scanning system in this particular process and controlled by elevator mechanism, which is lowers at the completion of each layer. So here is the process. So this is the schematic of stereolithography, where you can see a laser is coming and falling on the material, and the elevator is dipped into the resin. So resin, because it's a liquid based rapid prototyping system, so whatever the thickness is required, accordingly we can program this particular process. So here is a video. So with the help of this video, you will be able to understand this fundamental process.
Hello friends, in this video let us learn about stereolithography apparatus, that is SLA technology. This SLA technology also called as photo solidification, optical fabrication and resin printing. This SLA technology also fabricates the object layer over layer. In 1992, 3D Systems developed this SLA technology. This SLA works under a photochemical process, that is raw material will be in the form of liquid. That's a monomer and oligomer combination liquid. When UV rays falls on that liquid, it gets polymerized. The only process which makes that transparent object, that is SLA. Investment casting patterns also we can able to make by using this SLA technology up to the 20 micron accuracy. These are the reason we need to focus on SLA technology. Now let us see the list of components that is used in SLA technology. Resin tank. This is the main component for SLA technology. This resin tank completely filled with the combination of monomer and oligomer. Elevator. This elevator is used to guide the movable platform in Z-axis direction. XY scanning mirror. This XY scanning mirror focuses the UV rays on the liquid. Beam focusing optical, laser source, computer hardware, and sweeper. These are the major components. Normally, the tank completely will be filled. This sweeper is used to wipe the liquid over the build platform to make a uniformity. And this build platform moves in Z-axis direction. With the help of this elevator, this XY scanning mirror focuses the UV rays on the liquid. Laser source, here the UV rays will be generated, and these UV rays focused by the beam focusing optical, and it falls on the XY scanning mirror. Based on this XY scanning mirror angle, the light rays focus on the liquid. These are the function of this component. First step, we need to design the component by using computer software, and it should be sliced into a horizontal layer, and the digital code will be generated. This digital code will be given to the SLA printer. First, the bed will be in initial position at the top. After giving the input, it will move step by step down to the liquid, and it will stay below the liquid level. That height depends upon input layer thickness. Suppose we are giving 0.1 millimeter thickness, this bed will stay below the 0.1 millimeter thickness. This sweeper spread the liquid over the platform. After giving the input, EV radiation focused on a photopolymer resin with the help of CAD software in desired shape. Our object is built over the platform. After completing the successful first layer, again the build platform moves one step down. That height is our layer thickness. Again, the UV rays focus on the liquid in desired shape. Next layer will be formed. This process repeats until the object completes. After completion of the object, the bed will moves up and stays there to drain out the remaining liquids. Then the object is removed from the build platform. It taken away from the platform. These are the steps to be followed to fabricate a component by using this SLA technology.
So this is how the thickness of an object is obtained in this particular process, that is stereolithography. And obviously we have to perform some post-processing techniques over this part, which we fabricate using this process. And the other thing is how we are actually converting the resin into solid part. So that is the most important factor here. So here they are using UV rays for the same purpose. So this is how they are changing one form, that is liquid, which is a material, raw material, into the solid form by using. That is why it is called this photoresin technique. So here is another one. So similarly, we have this technique where we use powder as a raw material. So in the previous case, we were using a liquid as a raw material. So here in selective laser sintering, we are using powder form in the initial stage, and obviously we have to convert that powder into solid form. So I will be not discussing this part. So these are some basics. And similarly, we have the third one, that is solid rapid prototyping systems. So under these systems, here I have quoted one example of laminated object manufacturing. So lamination, you all know what is lamination. So here we have material. So obviously for lamination, a sheet is used, so that sheet is a solid material. So obviously the same or the similar material here we have to use if we want to fabricate a part or any component by using this process. So that will act as a stack of those laminated layers. So you have to uh, fabricate a part layer by layer, and the raw material which we are using here is in the form of solid itself. So this is the example of the third system. Now coming to the additive manufacturing process from the research point of view. So here on this side I have shown some traditional additive manufacturing processes like rapid prototyping manufacturing, rapid biomodel manufacturing, direct metal manufacturing, rapid mold manufacturing. So these are some traditional additive manufacturing processes. And on the other side, so based on the sources, the energy sources, we have derived some of the other processes which can be integrated with the additive manufacturing, like thermal spray is one of them, then physical vapor deposition, PVD, then chemical vapor deposition, arc welding. So these are some common terms. Hard facing. So hard facing, it is nothing but a welding, we can say. Then hybrid manufacturing, joining, and the last one is CSAM. So CSAM is cold spray additive manufacturing. So cold spray is one of the thermal spray spraying technique, and this has already been integrated with the additive manufacturing. So that is why it is a combination of two processes, like CS is cold spray and AM is additive manufacturing. So here in this particular figure I have shown the generalized additive manufacturing processes along with the additive manufacturing emerging technology based on the allied energy sources. So we can integrate all these techniques with additive manufacturing. First is thermal spray, PVD, CVD, arc welding, hard facing, hybrid manufacturing, joining. So here I want to quote one example, like if I talk about a flame. So where we can use flame. So flame is used for the cutting purpose. Like in welding, what we can do with the welding, we can perform cutting as well as we can perform the joining. So similarly here, these are the processes which I have mentioned here: thermal spray, PVD, CVD, arc welding, hard facing, hybrid manufacturing. We can integrate these processes with the additive manufacturing process for the fabrication purpose. Like flame can be used for the deposition of a coating also. So flame spraying is one of the dedicated thermal spray coating technique where we can use a material in the form of powder, and we can deposit that powder by melting that powder on some surface to form a layer that is called coating. So that flame is also used for cutting purpose. So similarly, there can be multiple applications for one process if we integrate that process with some another process. Now, so again, here I have represented cold spray technique, which I have already mentioned is one of the thermal spray coating technique. So this can be integrated with additive manufacturing, and here we have collected the recent studies on cold spray and cold spray additive manufacturing. Like this data which you are able to see in figure B, this one. So here these publications have been taken from the Scopus database. So what we have to do, we have to put the keywords into the Scopus database to search the number of articles which are based on some specific topic. Like here, if I want to search articles on cold spray, then what we can do, we can simply write cold spray technique or cold spray thermal spraying using cold spray additive manufacturing, like this. So we can search publications by keywords. So here you can see cold spray is the latest and emerging technology in thermal spraying, and this has been integrated with the additive manufacturing uh, due to some reasons. I'll quote those reasons later on. But you can see the graph, it is continuously increasing, and the number of publications, like here we have mentioned up to only 2021, because this paper was written by Dr. Gaurav Prashar in 2021. And if you search this particular topic in Scopus database, then you will get to know the papers are increasing as compared to the recent years. And in research, we consider 1 decade, like the data from last 10 years. So what we can do here, we can consider a data from 2015 to 2025, if you are interested to work on this particular topic. So it was started in 1980, but with the approach of deposition of metals, where because it is very difficult to apply a coating of metals, because it has ductility, lower melting point, as compared to the composite materials and other materials, like other refractory materials having high melting point. So there was a challenge, and this new technique was introduced in 1980. But now, if we are talking about 2025, so this technique uh, has already been integrated with the additive manufacturing. So that is the recent advancements, you can say, in the field of additive manufacturing. CSAM stand again, I'll repeat, CSAM stands for cold spray additive manufacturing. Now these are the typical components fabricated using the cold spray additive manufacturing process. Like here you can see in the figure 3, this is a rocket nozzle. So here in the first application, we can fabricate such parts by using some other additive manufacturing processes also. But here I am talking about the integration of thermal spray with the additive manufacturing. So this has been manufactured by using cold spray additive manufacturing technique. So this is a rocket nozzle, and particularly these particular nozzles increase the exit speed here. The like the internal pressure of the combustion chambers, and what it can do, like it can improve the thrust. So here basically it is used in the combustion process of the rocket engine. And these nozzles are very difficult to manufacture. As I said in the previous session, the number of degree of freedom which is required by using non-conventional processing techniques, that is very high if you want to manufacture such complex shapes. So but with the help of cold spray additive manufacturing, and you can say additive manufacturing techniques, so these can be produced in a very short time. And here is the another example that has been mentioned in the this figure B, that is the titanium housing, and here is the manufacturer of this housing. So this is a rotational casing, here you can see. So basically these type of rotational casings are used in aircraft engines, then in gas turbines, pumps, and even in wind power plants. So what are the challenges? Like if you want to manufacture this, otherwise how we manufacture such parts? Obviously by casting. So that is the conventional manufacturing technique which is used for such complex shapes. So we go by the casting process. But you know, casting of some metals and alloys are very difficult. It is easy in case of cast iron and their further types. But if you talk about some dedicated materials like titanium alloys, magnesium alloys, then the casting is very critical. So in that case, you have to go by those processes which can easily manufacture such complex shapes. So CSAM is one of them. Other manufacturing additive manufacturing techniques are also there, which can be used to manufacture such complex shapes. Moreover, here in this case, in this particular case, so production is usually a combination of several processes. Like you have to perform turning by using single point cutting tool. Then you have to perform milling operation with multi-point cutter, obviously. So large portion of the material is removed by turning and milling processes. So there is a wastage of material. So I always mention 2 points. So by using additive manufacturing technique, we can avoid a wastage of a material. And second, we can fabricate complex shapes. And further, here, cold spray additive manufacturing is used to create these contour of the components close to the final shape of the housing. And that is uh, with very small tolerance. Because like if we go with the casting process, obviously we have to perform many operations post casting. So here we can avoid those post processes. Like if we have very small tolerance, means the semi finished component can be completed by turning and milling on the required functional surfaces, where in this case we can directly fabricate a part with very small tolerances. So these are the 2 examples which I have selected for this presentation. That first is the rocket nozzle, which is used in the rocket engines, basically to increase the exit speed, where the internal pressure of combustion chambers improve the thrust as well as the combustion process of the rocket nozzle. And the second one is the rotational casing, which is particularly used in the aircraft engines, gas turbines, pumps, and wind power plants. Further, now in the additive manufacturing, like we use liquid, we use solid, and we use powders. So because I am talking about cold spray additive manufacturing, which is directly linked with the thermal spray, so here we use powders. So powders as a feedstock material. Like here you can see in the first figure A, here the particle is coming out of the nozzle. So because when we have to spray uh, any material on some surface, so we required high velocity, and for high velocity we have to use nozzle. So so that is why here we have mentioned nozzle. So the powder particles are coming out of the nozzle, which you can see in this first one, uh, in this case, and striking on the substrate material where you want to deposit this material, or you can say where you want to deposit this powder material. And in the second part here, the velocity of this one is very high. Here in cold spray technique, the velocity is maximum as compared to the other processes. So that is why the supersonic speed is mentioned here. The particles impacting at the surface at the supersonic speed. So there will be a plastic deformation of the material when it strikes on the surface, which can be seen in this figure B. Here you can see. So it is getting contacted with the surface, and here you can see a group type which is formed. So this is basically not a groove. So here the plastic deformation has held, and finally when it impacts on the surface with full velocity, there is a complete plastic formation by a kinetic compaction. Here you can see, because the another particle is also coming after this particular particle. So the number of particles are coming and striking on the surface to form a layer. So this layer is very compact. So this is a very compact layer because the powder particles are continuously coming out of the nozzle with very high velocity and striking on the surface and getting plastically deformed to form a layer one over another. So in thermal spraying, basically we call this layer by layer formation, and one layer is also known as splat. So this is also called splat by splat formation. So because we are particularly dealing with the powders, so here we have to use powders for the fabrication of the parts. So the powders which we have to use for the fabrication, so those can be produced by three methods. So here now we are very concerned about the raw material which we are using. So these are the three processes which are used for the manufacturing of the powders. First is the atomization method. Here you can see this is the atomization method. Second is the spray drying. So this is the spray drying, which is basically called fusion and crushing. So here is the fusion and crushing, and in the first one, that is automation method. So there are two techniques which used for the fabrication of powders. First one is the top to bottom technique. Second one is the bottom to top technique. Let us say you have a piece of a metal and you want to convert that piece of a metal into powder. So that is one of the methods. Otherwise, what you can do, you can also crush that particular material. So these are the two techniques, and for the production of powder you can follow these three methods, that is automation method, spray drying, fusion and crushing, because this is very important, one of the key parameters while selecting the material. So because it is particularly mentioned, if you are using a powder, so which method has been used for the production of this powder, that has already mentioned on the catalog, which for the parts which you want to manufacture. Let us say for aerospace engineering you want to manufacture a part. Let us say in some cases you want spherical shape, and in some cases you want irregular shape, and in some cases you want a mix of these two shapes. So that depends. Like here you can see. So here is the example. In the powder properties, you can see in the first SEM, this is one of the SEM micrograph where you can see the morphology of a powder. So here the particles are more likely spherical in shape. In this figure A. So these are the powder particles. This is the SEM micrograph taken from the powder. And here the magnification has increased. Here you can see this is a one particle only, and if you further magnify this, you will get to know about the distribution of the small particles, that is the clusters. With the help of these clusters, this one particle is formed, and here in the figure 1 you can see a number of particles. So characterization of the material is also very important. If you want to check your material, what is the shape of the material, what is the size of the material, that plays an important role. So why? Because how we categorize materials on the basis of size, obviously conventional sizes, then nanomaterials are there. Sometimes combination of conventional size and nanomaterial is there. So sometimes we call it micrometric and nanometric sizes. Sometimes we call it nanometric form, micrometric form, then micrometric size, nanometric size, and the combination of these two. So these are very important to know the morphology of the raw material by using field emission scanning electron microscopy, that is SCM. So you have to characterize your material also to get to know, if you want to get to know the shape and size of the material. Like we know nanomaterials are better than the conventional materials. Then obviously, but whenever we perform any whenever we want to initiate some process, like we have to use some raw material in that, but before using that raw material you have to characterize that material also. And phase composition and chemical composition. So electron dispersive spectroscopy, EDS, or which we call EDAX, that can be used to know the composition of the material. That gives you an idea about the composition of the material. And if you want to know the phase composition, that obviously you have to go by the X-ray diffraction analysis, that is XRD analysis, if you want to know the phases present in the material. So before using the material, you have to characterize the material, and some standards are there if you want to test your material for flowability and density. So these are the standard codes which you have to follow. Accordingly, you can test the flowability and density of the powders. So here I want to code powders only. Then here you can see in the fundamentals, because we have integrated thermal spray with the additive manufacturing technique. So what is the fundamental working behind the thermal spraying? So thermal means heat, spraying means you know what is spray. So whenever we use spray, so that is in the form of mist or some other form. So in that spray, so this is a flame which is coming out of the nozzle, and in this flame you can see some particles. So these are nothing but the powder particles. So these powder particles are heated with the help of this flame, and finally gets deposited on the surface of the component where you want to coat this particular material. So otherwise here you can see here is the substrate material on which you want to coat your material. So here the powder particles in orange color, so these are coming and striking on the surface, then it is getting deformed, then another particles are coming, getting deformed, another particles are coming. So in this way layers are formed. And similarly, in case of CSAM, that is cold spray additive manufacturing, you can fabricate a part by using this fundamental technique. But the additional part is the programming. You have to program that particular apparatus, and the nozzle will run accordingly to fabricate a process, to fabricate a part or component. So these are some other nozzles which are used, like other than cold spray, there are other methods also: plasma spray, then FS stands for flame spray, wire flame spray, arc spraying, HVF spraying, detonation gun. So there are different classes of material, and further when we club those classes, then we'll get composites, because this session is all about the composites. So when we combine two classes of a material, then we'll get composites. Like when we add ceramics into the metals, then those are ceramides. We can call them composite materials. So depending upon the melting point of the material, like in metal and alloys, the melting point is around 1500 degrees Celsius. And in case of ceramics, it can go beyond 2000 degrees Celsius also. Like we have materials, refractory materials, like aluminum oxide is there, silicon carbide is there, then tungsten carbide is there. So these are basically carbides, oxides, and nitrides. So these are the three types where the melting point can go beyond 2000 degrees Celsius. So depending upon the melting point of the material, you select the process which you want to integrate with the additive manufacturing, or you want to use for the deposition of the coatings. So that is why these different flames have been designed for the different materials. So here I want to quote this particular example, that is plasma spray. So if you want to deposit a material with very high melting point, then you have to go by the plasma spraying. On the other hand, if you want to coat a material that is a combination of metal and alloys and ceramics, then obviously over there you are mixing the materials in some quantity, like let us say 50% metals are you are using 50% metals, and rest of the 50% belongs to ceramics category. So in that case the temperature comes into the medium range. So because obviously for the metals it is near to the 1500 degrees Celsius, and in case of ceramics it is around 2000 degrees Celsius. So on an average, it is around 16 to 1700 degrees Celsius. So there is a range. So it comes under the medium range category. So you can go by the HVF technique. So that is why these different nozzles have been designed for different materials which you want to coat, and every material has different melting points, so you have to use different nozzles. So here you can see coating buildup. So coating buildup is similar to the uh, because this is the morphology of the coated surface. Let us say a powder particle is coming out of the nozzle and striking on the surface, and then finally it gets plastically deformed on the surface in the form of layer, or you can say splat. So those splats can be seen, but uh, due to the uh, temperature melting point difference, because if you are adding two materials together, let us say on one side you have nickel, that is a metal, and on the another side you are using some oxide, uh, like silicon carbide is a carbide, aluminum oxide is an oxide, then titanium nitride is the nitride. So if you are adding any of the ceramic material into the pure metal, let us say nickel, chromium, iron, cobalt, or any other metal, then there is a mismatch in the melting point, of that material. And other than the difference between the melting point, there is a difference between the coefficient of thermal expansion. So that is also uh, uh, a mismatch. So in that case, some particles remain unmelted. So here you can see on the surface, which we have highlighted in this one, this square and this oval shape. Like, so these are the unmelted powder particles. So why they are unmelted? That is due to the difference in the melting point of the materials, because this is a cold coating buildup of a composite material where we have added two materials together. So these are some of the challenges in composite materials. So in case of part buildup, when you are using cold spray additive manufacturing, so this is how the layers are getting deposited on the surface, or you can consider this one as a bed also, not substrate. Let us say this is the first layer. Here powder particles are coming. So this is the first layer. Here it is. In the second part, you can see the particles deformation and realignment. So based on the availability of the space, so these particles are as adjusting themselves into the available space, into the voids, you can say. So here we can use this, it is not appropriate to use this term void, but still here in this case we can use this one, empty space or voids. And here is the third one. Now particle bonding and void reduction can be seen here, because they have already been deformed and realigned in the second part. So that can be seen here. Now you look at the first layer in this one, again first layer in this one, and again first layer in this one. You can see the change in the shape of the powder particle. So because heat is also involved in this case, so due to heat, so it is already heated, and another particle with very high velocity is coming and striking on the first layer. So that is why completely deformation can be seen in second, third, and fourth. And here is the further deformation. Why further deformation? Obviously there is a continuous striking of the particles over each other, and that is called hardening basically. Last step. So this is the part buildup mechanism of a cold spray additive manufacturing, which is applicable in case of ductile materials, because the fabrication of a composite material is very complex. We'll discuss that also. Now coming to the conventional coating technique, because we are integrating that technique with the additive manufacturing. So this is the surface which is obtained after the deposition of a material on some surface. So here you can see here, some unmelted particles can be seen on the surface. But if we increase the process temperature, like here, you can see the process is HVOF. So it is used to deposit materials with medium range temperature. So that is why these particles remained unmelted. But in this process, you can see that is a plasma spray, as I mentioned in the previous slide. This slide, sorry. Here, plasma spray technique is used for the deposition of materials with high melting point. So these here on this surface, so there are very few unmelted particles because we have increased the temperature range. For the, if the melting point is high, then obviously what we have to do, we have to increase the temperature accordingly so that we can get less number of deficiency on the surface or in the material. Then here, if we compare cold spray additive manufacturing with the other techniques, now there are other techniques which are used, like thermal spray is one of them. Thermal spray is one of them which is used to produce the layers. And if you want more thickness, then you can go by the cladding process. So where thick layer can be produced. But you can utilize these two processes, that is coating and cladding, with the additive manufacturing to fabricate a part. Now here I am not talking about the thickness. Here I am talking about the fabrication of the part, as I mentioned in this slide. So these are the processes which are mentioned on this side, can be integrated with the additive manufacturing for the fabrication of the parts. Like in the first one, thermal spray, it is used to produce layer, a coating. Second, PVD. So PVD and CVD. So top to bottom approach, bottom to top approach. Here it is used where we have a coupons of material, and with the process of atomization, we are converting those coupons into the atoms, and that atoms are getting deposited on some surface to form a thin layer, a very thin layer, that is in nanometers. Then arc welding, you know arc welding very well, hard facing. So hard facing, it is used for the cladding purpose. So cladding means thick layer. So likewise, joining is hybrid manufacturing, is where n number of processes are coming together to form or to fabricate a process. Then joining is obviously wherever you are joining some materials, two parts together. So similarly, coming back to this one, so if we compare these two processes with the other techniques, here the deposition rate is very high. So because we are using powder as a material, and we have to put that material into the powder feeder, and the nozzles which we are using, the velocity of the powder particles is in the range of supersonic. Then with this very much high velocity, we can get metals into the action, because it is very difficult to reshape the metal because of its ductility, because temperature is very less in case of cold spraying. That is why it is called cold spray, because here the temperature is very less. So we are not integrating the plasma spray and HVF process with the additive manufacturing. We are integrating cold spray. So cold spray doesn't mean the temperature is in -degrees. So cold spray means the minimum temperature which is used in the thermal spray technology. So that is around 6 to 700 degrees Celsius, or you can say 500 to 700 degrees Celsius. Like if you want to deposit aluminium, so the melting point of aluminium is very less, but on the other side, ductility is very high. So those type of materials can be deposited by using this technique. And further, because the deposition rate is very high in this case. Deposition means if you are feeding 1 kg powder into the feeder, how much material is getting deposited on the surface? Let us say 500 grams. So that is called deposition process, deposition rate. So here the deposition rate is very high. So that is why this process is preferred over the other processes like laser sintering, powder cladding, wire cladding, e-beam, 3D welding, and even thermal spray processes. These processes. Then, so as we are integrating coding and cladding with the same, so these are some of the techniques where you can see cold spray nowhere. Why nowhere? Because it is one of the latest technologies in the thermal spray. Otherwise, we have vapor deposition. So these categories, CVD, PVD itself, then their extended versions. Plasma assisted CVD, again plasma assisted PVD. These are used to develop a thin layers. But here we are interested in the fabrication of parts, not thin layer, right? Then sol gel and electrochemical solution state. So these are another very famous techniques. Like if we have to use a shiny layer of a material over the metals, like spanners are the examples. Uh, so electrochemical galvanization process is there, which is used. Then coming to the third one is the molten or semi-molten state, where we use welding processes. Then laser technique is there, and the last one is the thermal spray. But here these are used for coating and cladding purposes only. So the new technique which has been introduced to this category is cold spray, which we have already integrated with the additive manufacturing process. And this is the difference, how these techniques are different from each other. And if you check the deposition rate, here is the deposition rate, kilogram per hour. So it is very high for these techniques, and especially in case of thermal spray. So why we are integrated additive manufacturing with thermal spray? So this is the second last column, thermal spraying. So you can see the deposition rate in kilogram per hour is very high, that is up to 10. Then coating thickness, look at this. So this coating thickness is in microns. Like, so the maximum thickness is in case of welding. Why welding? Because claddings are there. So you can deposit a cladding also. Dr. Gurpage is also working on microwave cladding. So he is capable of producing a layer of 2 mm, 3 mm. But here in case of thermal spraying, we deposit a layer of, let us say, 500 microns at max. Otherwise, in case of wear and erosion, because surface engineering is more likely related with the wear and corrosion applications. So in wear and corrosion applications, we use a layer of 2 to 300 microns only. But if you want to develop a layer, let us say you want to develop a thick layer over the rollers which are used in the cement factory. So over there you have to use hard facing. So that is why electrodes, welding electrodes are used over there for the remanufacturing process, for the repairing process, because thick layers are required over there. So that comes under welding. So otherwise we call that cladding, because there are two terms, coatings and claddings. So cladding comes under this category. Then this is the process which can provide a maximum thickness, but can't fabricate a part, can't fabricate any component of a machine or component of any other machinery. So uniformity, these are the parameters related to the coatings only. But the thing is, why we are showing this particular slide? Because of its deposition rate. So deposition rate, the material which we are using, the material which we are feeding, that is very high. Means if the deposition rate is high, the wastage is less. So this is the main parameter. Then these are the materials which can be used, like for wear resistance applications, where is the direct contact of the materials with each other. So these like tungsten carbide, cobalt, uh, this is the material which is used for the room temperature applications. So their extended versions are already there: tungsten, carbide, cobalt, chromium. Then you can further integrate this particular process with the laser texturing. So you can perform laser texturing on the surface, and then you can use this particular material on the surface. Similarly, if you want to join two parts together by using some means of additive manufacturing, then even you can use some pre or post treatments on the surface of the two parts which you want to join. Like laser texturing is one of them. Then micro drilling is one of them, where we produce grooves intentionally to release the stresses in the component or in the part of a machine or machine tool, right? Similarly, the extended versions of materials are available, but these are well-known materials. Like here, we cannot alter the composition of the materials. So these are patented materials which can be used in the application. Like here, the second material which I am which I mentioned, WCCO, tungsten carbide cobalt. So this material is extensively used in application. So wherever you go in the industry, where there is a use of thermal spray, coating or cladding, you will find its application for sure. Because it is used for the room temperature applications, where two surfaces are in directly contact with each other, and um, the property, the mechanical property which is required over there is the hardness. That is the ability of a material to resist wear, then penetration and scratches. So for that purpose, you can use this particular material. Otherwise, if you are interested in some other particular applications, then you can use some other recommended or patented materials, like Al2O3 TiO2, that is aluminum oxide, titanium oxide. So many of you may be familiar with this particular material. There are two forms available in the market. One is the I think 14% of titanium oxide and 40% titanium oxide, something like this. So there are two combinations, patented combinations available in the market for heat resistant applications. Similarly, chromium, carbide, nickel, chromium, the third material in second point, and YSZ thermal barrier coatings. That is yttrium stabilized zirconia. So which is used in thermal barrier applications. So wherever there is a example is radiator. So in a radiator, it is used for the cooling system. So walls are there. So heat is getting dissipated because water is circulating in the pipes of the radiator. So what is actually happening over there? Heat dissipation. But in case of internal combustion engine, that dissipation is not required. That is the requirement for the efficiency. So heat is required over there. So to avoid the heat loss, we have to use some thermal barriers. So this material is widely used, that is yttrium stabilized zirconia. And other than this, there are some other materials. I recently came to know about those materials. Those are refractory high entropy alloys materials, because we are in a process of filing a project in ISRO. So they have mentioned some application, that is ultra high temperature application, where the minimum temperature is 1500 degrees Celsius. Like because we are talking about composites. So where we are using composites, where we have to use composites. So composite materials are obviously specially designed materials. So this is not a pure class of a material. So it is a combination of some classes of a material. So composites, when we are talking about composites, it means we have to use that material for a special purpose, where multiple set of properties are required. So here, if multiple set of properties are required, then you have to tailor the properties of the material by using the composites. So here, most of the examples are related to the composites only. Like Cr3C2 NiCr is an example of a composite material. So where nickel, chromium, metal. Nickel is metal, chromium is metal. Then chromium Cr3C2 carbide. It is a chromium carbide. It comes under the category of a carbide. Similarly, aluminium oxide, titanium oxide. Then here, uh, uh, here is a class of metal and alloys, that is tungsten carbide, cobalt, chromium. So temperature is again very important parameter, because if we keep on increasing the temperature, but we are compromising with the materials also. If the temperature is excessive, then we may lose the actual properties of a material. If you are depositing if you are depositing a layers by using a material, that material is obviously a powder in this case, by using a powder. So in that case, there may be a chances of material degradation due to high temperature. So you may lose the actual materials property. So that is why temperature control is required. But on the other side, deposition rate is also important. So here you can see the temperature. In this case, plasma, HUF, flame spray, and this one. So temperature is very high. So as I said earlier, in cold spray it is around 600, 700. Sometimes it is less than 500. 400 to 700 you can conclude. In between 400 degrees Celsius and 700 degrees Celsius. So the temperature is very less because we have to avoid the material degradation also due to excessive temperature. So that category has already been introduced in this particular case. Then characterization techniques. So some characterization techniques we can use. So these are very common techniques. You all are familiar with the metallurgical characterization, where we perform XRD, porosity, FESM. When you are done with the fabrication of a component, then you have to check its microstructure, you have to check the morphology of the material. So these techniques can be used. Then you have to perform mechanical characterization, like in the form of hardness, where we use Vickers hardness. Then we also use other 3-point bending tests is there. Then fracture toughness analysis is there. Then scratch test is there. There are many more others which can be used, not only for the coatings, for the fabricated parts. Like here, it is a combination of powder and fabricated surface. So powder is in the form of spherical shape, here in figure A, where in figure C and D, in C you can see some unmelted powder particles. In D, if we further magnify it, then you will be able to see the completely melted zones, which are basically very flat zones, very smooth. This is also known as a smooth zone, smooth surfaces. So melted zones are corresponding to the smooth surfaces, which can be seen by using FESM, field emission scanning electron microscope. And further, its composition can be analyzed by using EDS. Here you can see the elements which are present in the particular material. Then microstructural analysis can be performed by using EDS. The elements which are present in the material, how they are segregated over the surface, and then over the component, over the surface of the component, you can analyze by using X-ray mapping, or you can say sometimes it is called EDS mapping also. It can be performed on this only. on this particular apparatus, which we call FESAM apparatus. So here is one attachment provided by Oxford Instruments. It is used for the calculation of composition, that is very famous with EDS, and this mapping can also be done. How the elements which you are using in a composite material on in any alloy are distributed over the surface. Then now talking about specific applications, here are the some materials and how they are contributing to the actual applications. Like in case of gas turbines, which materials can be used here? Some materials have been mentioned which can provide oxidation resistance as well as erosion resistance. Then for these applications you can use these particular materials, and obviously additive manufacturing is widely used in the fabrication of biomedical implants. So over there the material which is used is calcium phosphate, which is very much famous with the name of hydroxyapatite, that is HAP. So you can use this material also for the fabrication using 3D printer or cold spray additive manufacturing. So we have one research article on this also. Then here are the materials, their operating temperatures and their applications. So here you can see some pure ceramics, then alloys can be seen, composites can be seen, and super alloys can be seen. Like Inconel 718, Inconel 625 comes under the category of super alloys, which are used for the oxidation and erosion resistance. Then now coming to the advances in material technology, what industries are basically facing. So wear and corrosion, these are the famous issues in every industry, because whenever any surface is exposed to some environment, then there may be a degradation, either due to the chemical reaction or due to the mechanical action. So these two terms are linked with the chemical and mechanical action. So wear related problems due to long working hours and severity of the working conditions. So there is need to develop a new materials. So because many of us are doctorate, so we have already done work on these different materials during our masters and doctorate program. So we have developed different materials, like in some case conventional materials, in some case nanomaterials. Sometimes we compare these two materials, sometimes we fabricate a combination of these materials, sometimes we integrate different classes of materials with different sizes. So but the ultimate requirement is the research and invention of advanced materials. So nanomaterials are one of them. Hall pitch relation is very important. When the grain size decreases, so obviously the strength increases. Which strength? Yield strength increases, hardness increases, wear resistance increases, fracture toughness increases, and other required properties are also in this list, right? So these are some of the materials which can be used, like high entropy alloy. These are very famous materials, bimodal materials, where you are combining a form of a conventional material and nanomaterial. Then cold spray is the one of the latest coating technique. And finally, the cold spray additive manufacturing, where we are combining cold spraying with the additive manufacturing process. We give program which is linked with the cold spray setup, and that according to that program, it starts building a product or part or component which is to be manufactured. So that is there. So these are the famous journals which you can refer, where you can find out the publication related to these these advanced materials and advanced techniques, right? So surface and coating is one of them. You can find papers related to the cold spraying additive manufacturing in these three journals. So these are very famous journals related to the surface engineering. Then here are some studies which we have gone through, like this is the high temperature, because we are basically dealing with the high temperature applications. So we use super alloys, here in this particular case. Then second again, composite material, where we have used metal with the ceramic, so ceramic coating. This is basically ceramic coating. So here it is a pure superalloy coating, but there was a bond coat introduced between the top surface and substrate material. Then here is the further extended form, where we have used the bi-model composite coatings. So published by Dr. Gaurav Prashar, who is also here in this session. Here again, this is related to the cold spray additive manufacturing, written by Dr. Gaurav Prashar. So here, what we have introduced in this particular paper. This was published in 2021 in Journal of Cleaner Production. Our main focus was on the green technology, because we came to know about the sustainable development goals and its importance, near 2021 2022. So these topics came into picture in these years. So we focused on the same, and this was our first publication, where the impact factor was 10 plus. And here we have elaborated the the state of art, this, because this was in the initial stage at that time in 2021. There were, I think, only 2-3 papers available on this technology, and what are the challenges and what are the future challenges as well. So we have incorporated everything in this particular publication, that was published in Journal of Cleaner Production. Then these are some other techniques which can be integrated with the cold additive manufacturing. Here this was published by Dr. Gurpreet Singh, who is a coordinator of this particular ATAL-FDP. So this is a very good publication. We have elaborated about the thick layer, how thick layer can be produced in this particular application. Then this is our recent publication, because we are more likely targeting biomedical implants. So this is the publication of 2025 by my research scholar, Parveen Kumar Verma. So I am guiding him as a co-supervisor. He is in Punjabi University, Patiala. So we are more likely focusing on the fabrication of biomedical implants. So that is why we are concerned about these materials, and hopefully we'll be trying, we'll be trying more likely about the fabrication of these particular parts, especially the parts which are manufactured by using this surgical grade, that is SS254. So this grade is basically used for the fabrication of many biomedical implants, and even for the fixation devices. Like if you have to fabricate a rib cage, then how that rib cage is fixed into your body, then you need some fixation devices also. So those fixation devices are nothing but the screws. Small cages are there with clamps and screws. So we are more likely to work on these biomedical implants and fixation devices in the future. So that is why we are studying the behavior of these materials, how these materials are behaving in different conditions, like at if we use some other processes like post processing, post processes with these materials, what should be the material of behavior of the material at particular temperature if we are post processing that material. So that is also another aspect of this study. But more likely, if you want to use any new material with a new process, then you have to initially perform some preliminary research on that material. So this is our preliminary research, and in the coming studies we'll try to integrate this particular with the additive manufacturing part. So last but not the least, I would like to thank all these. First of all, my supervisor, Dr. Harmeet Singh from GN, Guru Nanak Dev Engineering College, because the studies which I have shown belongs to these persons only. Dr. Lalit Thakur, my co-supervisor from NIT Kurukshetra, then Gaurav, Dr. Gaurav Prashar is also here in this session. Then Dr. Gurupesh Singh, Dr. Amrinder Mehta, and Mr. Praveen Kumar Verma. So I have used the sources from these studies, performed by these people. So this is all from my side. Thanks.
Good evening, Dr. Hitesh.
Good evening, sir.
Sir, very informative and elaborative talk by you. So, thanks a lot for all the key features which you have discussed about the nanomaterial based composites or bio implants. So, sir, I would like to ask one simple question. Maybe it will be simple really for you, but so how the toxicity and leaching behavior could be addressed in the case of the nanomaterial based composites or the material used for bio implants?
Hello, Dr. Hitesh, are you available? I think Dr. Hitesh is not available due to technical error. So thanks to all joining us, Dr. Hitesh. Also, I would like to thank you for this wonderful session, and participants. I would like thank you to all for joining us. Uh, Thank you once again.